What if I told you that the emptiest space in the universe isn't empty at all? That what we call nothingness is actually a bubbling, seething ocean of energy, a place where particles flicker in and out of existence so fast they defy everything we think we know about reality. Welcome to the quantum vacuum, one of the most baffling and beautiful mysteries in all of physics. It's not just empty space, it's a hidden realm where the rules of our everyday world break down, where energy dances in ways we're only beginning to understand. Scientists have spent decades trying to unravel its secrets, and what they've found will make you question the very fabric of existence. Picture this: every single cubic centimeter of so-called empty space, even in the deepest reaches of the cosmos, is alive with unimaginable activity. Particles appear from nowhere, vanish in an instant, and leave behind ripples of energy that might hold the key to dark energy, black holes, even the birth of the universe itself. The quantum vacuum isn't just a scientific curiosity, it's a frontier that could rewrite physics as we know it. And today, we're diving into 30 of its most mind-bending mysteries, from the eerie Casimir Effect to the shocking possibility that our entire universe might be floating in an even vaster cosmic ocean we can't yet see. This isn't just a story about equations and lab experiments. It's about peering into the heart of reality and discovering that the universe is far stranger, far more alive than we ever imagined. Whether you're a science enthusiast or just someone who loves a good mystery, what we're about to explore will leave you awestruck, because the quantum vacuum isn't just out there in space, it's everywhere, even in the room around you right now. So buckle up, we're about to take a journey into the hidden depths of nothingness and uncover why it might hold the answers to everything. Let's start with the first mind-bending puzzle of the quantum vacuum: zero-point energy. Imagine shaking a snow globe, watching the flakes swirl chaotically even after you've set it down. That's what empty space is like at the quantum level, a storm of particles and energy that never quiets. Quantum theory tells us this activity isn't just random noise, it's the universe's baseline hum, the energy that remains even when a system is in its lowest possible state, at absolute zero. But here's where things get weird. When physicists calculate the total energy density of this quantum frenzy, the numbers explode into infinity. Picture adding up every flicker, every virtual particle popping in and out of existence across all of space. The result should be enough energy to tear the cosmos apart. Yet when we look out at the universe, space appears almost empty, expanding gently under a tiny cosmological constant. The mismatch between theory and reality isn't just off by a little. It's a discrepancy of 120 orders of magnitude. That's a 1 followed by 120 zeros, a number so absurdly large it's been called physics' most embarrassing failure. Scientists tried to fix this with a mathematical trick called renormalization, essentially sweeping infinity under the rug by subtracting it from equations. It works for practical calculations, but it feels like slapping duct tape on a broken dam. The deeper question remains: why does the vacuum's infinite energy not warp reality as we see it? Some suggest unknown symmetries cancel it out. Others wonder if we're missing a fundamental piece of the puzzle. One thing's certain: until we solve this paradox, our understanding of the universe's true nature hangs in the balance. If zero-point energy left you reeling, brace yourself, because the quantum vacuum has an even stranger trick up its sleeve. Between the endless churn of energy lies a phenomenon so bizarre it makes particles appear to materialize from pure nothingness. These are virtual particles, short-lived pairs of matter and antimatter that flicker into existence for unimaginably brief moments before annihilating each other. They're not just theory, they leave fingerprints on reality itself, and we've caught them red-handed. Take the Casimir Effect, one of physics' most jaw-dropping demonstrations of quantum weirdness. Place two uncharged metal plates extremely close together in a vacuum. so close that only certain wavelengths of quantum fluctuations can fit between them. Outside the plates, a frenzy of virtual particles of all sizes buzzes freely, but inside that narrow gap, only the tiniest fluctuations survive. The result: an imbalance of pressure that pushes the plates together with measurable force. It's as if the vacuum itself is squeezing them, proving that empty space isn't passive. It's a dynamic arena where particles dance in and out of existence, exerting real physical effects. But here's the million-dollar question. Are these particles truly real or just mathematical ghosts in our equations? On one hand, their effects are undeniable. They shape the behavior of atoms, influence starlight, even play a role in black hole radiation. Yet they defy direct observation, vanishing before any detector can spot them. Some physicists argue they're mere calculation tools, placeholders for deeper, unknown processes. Others believe they're as real as any electron or photon, just operating on rules we don't yet grasp. The implications ripple far beyond labs and textbooks. If virtual particles are more than math, they hint at an unseen layer of reality where creation and destruction happen constantly, where the universe borrows energy from nowhere to fuel its own strangeness. And if they're not, then our best models of physics might be masking an even grander mystery waiting to be uncovered. Either way, the Casimir Effect pulls back the curtain on a truth far wilder than fiction. That so-called emptiness is a stage for the most fleeting yet consequential performances in the cosmos. Now consider this: every time you touch a surface, virtual particles are at work in the gaps between your atoms. The very stability of matter might depend on these quantum apparitions. So next time someone calls space empty, you'll know better. It's a seething, shimmering sea of potential where nothingness is the most deceptive illusion of all. The vacuum catastrophe isn't just a problem, it's a screaming paradox at the heart of modern physics. Imagine calculating the weight of a feather, and your equations insist it should crush the entire planet. That's essentially what happens when physicists try to estimate the energy density of the quantum vacuum. According to quantum field theory, the sum of all those flickering virtual particles and zero-point fluctuations should fill every cubic centimeter of space with enough energy to warp spacetime beyond recognition. The math predicts a number so absurdly large, 10 to the power of 112 times stronger than what we actually observe, that it threatens to unravel our entire understanding of the cosmos. So why doesn't the universe tear itself apart? The observed vacuum energy, which drives the gentle acceleration of cosmic expansion, is almost inconceivably tiny by comparison. It's like expecting a hurricane and getting a whisper. This mismatch isn't just a rounding error, it's the largest discrepancy between theory and observation in all of science. Some call it the cosmological constant problem, others the vacuum catastrophe, but whatever the name, it's a glaring sign that something fundamental is missing from our equations. The crisis cuts to the core of physics' greatest unsolved puzzle. Quantum mechanics and gravity refuse to play nice. Quantum field theory treats the vacuum as a seething foam of particles, while general relativity sees spacetime as smooth and geometric. When we try to merge them, the numbers spiral into nonsense. Some theorists suggest hidden symmetries cancel out most of the vacuum's energy, leaving behind the faint trace we call dark energy. Others propose radical ideas like an undiscovered field that counteracts the vacuum's frenzy, or even the chilling possibility that our universe is one bubble among countless others in a multiverse, where most vacua do rip themselves apart, and we just happen to live in the rare stable one. The stakes couldn't be higher. If the vacuum energy were just slightly stronger, galaxies would never have formed, slightly weaker, and the universe would have collapsed long ago. This razor-thin balance hints at either a staggering cosmic fine-tuning or a gap in our knowledge so vast, solving it could rewrite physics from the ground up. Until then, the vacuum catastrophe stands as both a humbling reminder of how much we don't know and an electrifying clue that the answers might reshape reality itself. Now let's turn to something even more unsettling. What if the vacuum itself changes depending on how you move through it? Imagine you're an astronaut accelerating through empty space at nearly the speed of light. To someone watching from Earth, you're gliding through a quiet, particle-free void. But for you, things look very different. Your ship's instruments would detect a warm glow of radiation particles shimmering into existence where none should be. This isn't science fiction, it's the Unruh Effect, a phenomenon so strange it forces us to ask, is reality itself observer-dependent? Named after physicist William Unruh, this effect reveals that acceleration warps our perception of the quantum vacuum. Just as a car engine heats up when pushed to its limits, an accelerating observer effectively heats the vacuum around them, causing virtual particles to appear as real, detectable radiation. The faster you accelerate, the hotter this phantom glow becomes. For everyday motions, like driving a car or even launching a rocket, the effect is too faint to notice. But near light speed, the vacuum would blaze with particles as if you'd entered a cosmic sauna. Here's where it gets wild. The Unruh Effect isn't just a quirk of math, it's deeply tied to Hawking radiation, the eerie glow emitted by black holes. Both phenomena hinge on the same radical idea. What one observer sees as empty space, another might see as a particle-filled furnace. Near a black hole's event horizon, the intense gravitational acceleration plays the same role as a spaceship's thrust, conjuring radiation from nothingness. This parallel suggests something profound, that particles aren't absolute entities but emerge from the interplay between observation and motion. Could this mean the vacuum isn't a fixed backdrop but a chameleon, shifting its nature based on who's looking? Some theorists argue yes, proposing that reality itself might be a kind of cosmic illusion, stitched together by the observer's state of motion. Others caution that these particles are real only in a technical sense, mathematical artifacts of acceleration, like the way a spinning dancer sees the room blur around her. Either way, the Unruh Effect shatters our intuition about emptiness. It hints that the universe is far more fluid than we thought, with the quantum vacuum acting less like a static stage and more like a funhouse mirror, warping its appearance for every observer. So next time you stare into the night sky, remember, the void might not be so empty after all. It just depends on how fast you're moving. Einstein, Podolsky, and Rosen never imagined their thought experiment would expose one of the quantum vacuum's most unsettling secrets, that emptiness might be the universe's ultimate wiring system. The EPR paradox began as a challenge to quantum theories, spooky action at a distance, but today it reveals something even stranger. The vacuum itself could be a vast, invisible network where particles whisper to each other across cosmic distances. Picture two coins spinning in perfect sync. Flip one, and the other instantly lands matching, whether they're inches apart or light years away. That's quantum entanglement, and in the vacuum, it's not just particles that are linked. Entire fields might be communicating in ways that defy space and time. Laboratories have proven this isn't speculation. In experiments, entangled particles respond to measurements of their partners instantly, even when separated by distances so vast that light, the universe's speed limit, would take years to bridge them. It's as if the vacuum stitches reality together with hidden threads, bypassing the need for signals to travel. But how? One radical idea suggests the vacuum's zero-point fluctuations aren't random noise. They're the medium for this phantom connection, a kind of quantum Wi-Fi woven into the fabric of space itself. Critics argue this violates relativity's ironclad rule. Nothing outruns light, yet the math holds. Entanglement doesn't transmit information in the classical sense. It's more like two sides of a single quantum coin, flipping in unison no matter how far apart. Some theorists propose the vacuum's fields exist in a higher dimensional space where separation is an illusion, like 2 points on a folded sheet of paper touching without crossing the surface. Others wonder if entanglement reveals a deeper layer of reality where past, present, and future are fundamentally linked. The implications are staggering. If the vacuum is a web of entanglement, it might explain how black holes remember what they swallow, or how particles at opposite ends of the universe seem to share hidden knowledge. Could this network even hint at a cosmic consciousness, as some fringe theories suggest? More pragmatically, labs are already harnessing vacuum entanglement for unhackable quantum encryption, proving that spooky action isn't just philosophy, it's the next frontier of technology. So is the vacuum whispering secrets across space? The answer might redefine not just physics, but our very notion of connection. After all, if emptiness can bridge galaxies in an instant, perhaps the universe is far more intimate than we ever dreamed. At first glance, hydrogen seems simple, a single electron orbiting a proton, the textbook model of atomic structure. But in the late 1940s, physicists Willis Lamb and Robert Rutherford spotted something odd. When they measured the electron's energy levels with extreme precision, they found a tiny discrepancy, a barely there shift in its orbit that classical physics couldn't explain. This anomaly, now called the Lamb shift, became the smoking gun that proved empty space isn't just a blank slate. It's an active participant in shaping reality itself. The secret lies in the quantum vacuum's ceaseless churn. Even in a perfect void, electromagnetic fields fluctuate wildly, with virtual photons, the carriers of light, blinking in and out of existence. These fleeting disturbances interact with hydrogen's electron, subtly nudging its position like a leaf buffeted by invisible gusts. Over time, these micro-tugs alter the electron's energy state, creating the Lamb shift's telltale wobble. It's as if the vacuum itself reaches into the atom and rewrites its rules, leaving fingerprints on the very fabric of matter. What's astonishing isn't just the shift's existence, but its precision. Quantum electrodynamics, the theory governing light and matter, predicted this effect down to the 9th decimal place. When Lamb's experiments matched those predictions, it wasn't just a win for physics, it was proof that the vacuum's ghostly fluctuations have measurable, real-world consequences. Suddenly, nothingness became a dynamic force, one that cradles every atom in the universe, subtly tuning their behavior. Think of it like a guitar string vibrating in a storm. Even if you pluck it perfectly, the wind here, the vacuum's virtual photons, will bend its notes ever so slightly. For hydrogen, that bending amounts to just a few millionths of an electron volt, but that's enough to reshape our understanding of emptiness. The Lamb shift revealed that atoms don't exist in isolation. They're in constant dialogue with the seething quantum void around them. This discovery didn't just solve a puzzle, it rewrote the playbook. Without the Lamb shift, technologies like atomic clocks and GPS, which rely on hyper-precise atomic behavior, wouldn't work as accurately. It's a humbling reminder that even the quietest corners of the universe hum with hidden activity, and what we call empty is anything but. So next time you glance at the night sky, remember every star, every planet, every speck of dust is dancing to the vacuum's silent, eternal tune. We've danced through the quantum vacuum's wonders, but there's a shadow lurking in its depths, one so unsettling even physicists hesitate to say its name. What if the vacuum we call home isn't the lowest rung on the cosmic ladder? What if it's just a halfway point, a precarious ledge above an abyss of true nothingness? This is vacuum decay, the universe's ultimate existential crisis, where a single quantum hiccup could erase reality as we know it. Picture the vacuum like a frozen lake on a warm day, stable for now, but with cracks hidden beneath the surface. Quantum field theory suggests our vacuum might be metastable, a temporary arrangement where the Higgs field, the cosmic molasses that gives particles mass, isn't in its true lowest energy state. It's as if the universe is holding its breath, balanced on a knife's edge. If something nudged the Higgs field into a lower energy configuration, say a random quantum fluctuation, it could trigger a catastrophe. A bubble of true vacuum would form, expanding at light speed in all directions, rewriting the laws of physics as it goes. Atoms would dissolve, forces would unravel. Everything from galaxies to the very fabric of space-time would cease to exist. The numbers are chilling. In one scenario, calculations suggest such a bubble could already be racing toward us from some distant corner of the cosmos, its approach undetectable until the instant it arrives. There'd be no warning, just a wall of annihilation, rewriting reality faster than a nerve signal could scream, "Run." Now, before you panic, know this: the odds are astronomically low. The Higgs field appears stable for now, and experiments at CERN continually test its fragility by smashing particles at near light speeds, probing for signs of instability. So far, the vacuum holds, but here's the twist: even if decay were possible, we might never see it coming. The universe is so vast that a bubble could be born billions of light years away, already erasing everything in its path, and we'd only learn of it as the wavefront hit. Is this science or cosmic horror? Both. Vacuum decay isn't just a physicist's nightmare, it's a humbling reminder that the universe might not be built to last. Yet there's a strange comfort in that. It means every moment of existence, from the birth of stars to the light in your eyes, is a defiance of entropy. So the next time you sip coffee or watch a sunset, savor it. Against the backdrop of an indifferent cosmos, the fact that any of this exists at all is nothing short of a miracle. The quantum vacuum isn't just a stage for fleeting particles under the right conditions. It can cough up real matter from pure nothingness. This is the Schwinger effect, a phenomenon so audacious it makes alchemy look tame. Picture an electric field so intense it rips the fabric of emptiness apart, spawning pairs of electrons and their antimatter twins, positrons, like sparks flying from a cosmic anvil. In ordinary circumstances, these particles would vanish as quickly as they appear, annihilating each other in a flash of energy. But crank up the electric field to around 10 to the power of 18 volts per meter, a strength found near pulsars or in heavy ion collisions, and something extraordinary happens. The particles are torn apart before they can self-destruct, becoming permanent residents of the universe. Julian Schwinger, the Nobel-winning physicist who predicted this in the 1950s, showed that emptiness isn't just reactive, it's generative. The effect hinges on quantum tunneling, where particles borrow energy from the vacuum to briefly exist. Normally, they repay that debt instantly by annihilating. But in a field strong enough, the energy loan gets written off. The particles are yanked in opposite directions, gaining enough real energy from the field to escape their fleeting fate. It's as if the vacuum, stretched thin by extreme forces, finally snaps and spills its hidden contents into reality. Here's where nature outdoes sci-fi. Neutron stars, those ultra-dense corpses of dead suns, might be doing this right now. Their magnetic fields are so monstrous, quadrillions of times stronger than Earth's, that they could be continuously birthing electron-positron pairs from the void, fueling the intense radiation jets we see pulsing across the galaxy. These stellar powerhouses essentially turn nothingness into fireworks, proving Schwinger's math isn't just theory, it's woven into the cosmos. Could we ever harness this effect? Labs have recreated it momentarily using lasers, but scaling it to practical energy extraction is a pipe dream for now. The fields required are unimaginably intense, and the energy input far outweighs the output. Yet the tantalizing idea remains: if we could tap the vacuum's generative power, we'd have a near limitless energy source, literally creating fuel from empty space. Some theorists even speculate that advanced civilizations might have already cracked this trick, using Schwinger-like mechanisms to power their technologies. For now, the Schwinger effect stands as both a triumph of quantum theory and a humbling reminder of nature's raw power. It tears down the illusion that particles are fixed, immutable things, showing instead that matter is a temporary loan from the vacuum, one that extreme forces can call due at any moment. So the next time you stare into the void, remember, under the right conditions, it stares back with electrons. Imagine a force so mysterious it makes up 68% of the universe, yet we can't see it, touch it, or even explain what it really is. Dark energy, the phantom driver behind the accelerating expansion of the cosmos, might have its roots in the most unexpected place, the quantum vacuum itself. Here's where the story twists. According to quantum theory, the vacuum's energy density should be enormous, enough to curl spacetime into knots. But observations show dark energy's effect is whisper-thin, a gentle nudge pushing galaxies apart. The mismatch isn't just puzzling, it's a cosmic contradiction that keeps physicists awake at night. Let's break down the numbers. Quantum field theory calculates the vacuum's energy by summing every possible fluctuation between virtual particles. The result, a staggering 10 to the power of 120 times stronger than what we observe dark energy to be. It's like expecting a tsunami and finding only ripples in a pond. This colossal discrepancy, known as the cosmological constant problem, suggests one of two things. Either some hidden symmetry cancels out almost all that vacuum energy, leaving behind the faint trace we call dark energy, or dark energy isn't vacuum energy at all, but something entirely different. The plot thickens when we compare predictions to reality. Quantum vacuum energy should warp spacetime violently, yet the universe expands smoothly and uniformly. If vacuum energy were truly as potent as theory claims, galaxies wouldn't have had time to form before being ripped apart. Some theorists propose a delicate cancellation mechanism where positive and negative contributions from unknown particles balance out with near-perfect precision. Others, like Nobel laureate Steven Weinberg, once floated the eerie idea of anthropic reasoning, that we only observe a weak dark energy because a stronger one would have prevented life from arising in the first place. Then there's the multiverse angle. If our universe is one bubble among infinite others, each with its own vacuum energy, most might be inhospitable, either collapsing instantly or expanding too fast for stars to form. We'd simply find ourselves in the rare bubble where dark energy is just right, a cosmic Goldilocks scenario. But this remains speculative, a last resort for explaining the unexplainable. What's undeniable is that dark energy's fingerprints are everywhere. Supernova measurements, galactic surveys, even the cosmic microwave background all point to its existence. Yet whether it's a manifestation of the quantum vacuum's shadowy depths or something entirely separate, perhaps a new field or a modification of gravity, remains the greatest unsolved puzzle in cosmology. The answer won't just rewrite textbooks, it could redefine our understanding of nothingness itself. After all, if the void holds the key to the universe's fate, then emptiness is anything but empty. Imagine staring into the ocean at night, only instead of water, it's an infinite, churning abyss of electrons, each one a tiny whirlpool hiding beneath the surface of reality. That's the hauntingly beautiful vision physicist Paul Dirac conjured in 1928 with his Dirac Sea, a radical solution to a problem that threatened to upend quantum mechanics. His equations insisted electrons could have negative energy, a nonsensical idea implying atoms might collapse into infinite oblivion. So Dirac proposed the unthinkable: the vacuum isn't empty. It's a submerged ocean where every possible negative energy state is already occupied. According to this picture, what we call empty space is actually a perfect invisible plenum, with electrons packed shoulder to shoulder in an unfathomably deep cosmic reservoir. When an electron gets yanked out, say, by a cosmic ray, it leaves behind a hole that behaves exactly like an electron's opposite, a positron. Dirac didn't just solve his equation, he accidentally predicted antimatter. The discovery of positrons a few years later stunned the world, proving even his wildest metaphors could touch truth. But here's where history twists. Modern quantum field theory scrapped the Dirac Sea, replacing it with the cleaner mathematics of particle creation and annihilation. Today, we describe positrons not as absences in a hidden ocean, but as independent particles dancing with electrons in the quantum vacuum's dynamic ballet. The Dirac Sea became a relic, a stepping stone to deeper understanding, or so we thought. Yet something lingers. Strip away the outdated imagery, and Dirac's intuition still whispers the vacuum is full. Not with literal electrons, but with potential a roiling substrate where particles are excitations of underlying fields, like waves on an unfathomably deep ocean. Philosophers of physics argue the sea wasn't just wrong. It was too right in its insistence that nothingness is an illusion. After all, quantum field theory's vacuum teems with zero-point energy and virtual particles far stranger than Dirac's crowded basement of electrons, but no less filled. Could the Dirac Sea hold a deeper lesson? Some suggest it's a metaphor for how science progresses not by discarding old ideas entirely, but by refining their essence. Others see it as a cautionary tale. Our models of reality are always provisional, shaped by the mathematical tools of the time, and perhaps that's its greatest legacy. The sea reminds us that even wrong theories can point toward truth, that the universe's secrets often hide in plain sight, masked by the limitations of our imagination. So next time you hear empty space, think of Dirac's ghostly ocean. It's a reminder that the most poetic ideas in science, even those overtaken by progress, can ripple through time, leaving traces of brilliance in their wake. String theory may dominate headlines, but there's another contender in the quest to unite quantum mechanics and gravity, one that paints the vacuum as a tapestry woven from threads of spacetime itself. Loop quantum gravity dares to imagine a universe where emptiness isn't smooth and continuous but pixelated, with each pixel so small that a million could fit across a single atomic nucleus. Here, the vacuum isn't just active, it's fundamentally granular, a cosmic mesh where spacetime's very fabric is stitched together from finite, indivisible loops. Picture the universe as an infinite patchwork quilt. In Einstein's relativity, this quilt is perfectly smooth, a fabric that bends and warps without any underlying texture. But loop quantum gravity insists there's a hidden weave, tiny, vibrating loops of gravitational field at the Planck scale, each one a billionth of a trillionth the size of an atom. These loops knot together to form the network we call spacetime, meaning the vacuum isn't an empty stage, it's more like a dynamic spiderweb, with each strand humming with quantum energy. This radical rewrite of reality has staggering consequences. First, it banishes the infinities haunting black hole centers and the Big Bang. In general relativity, crushing matter into a singularity creates equations that explode into nonsense. But loop quantum gravity suggests these are just artifacts of pretending spacetime is smooth. At unimaginably small scales, the granular vacuum acts like a quantum cushion. Gravity grows weaker, not stronger, preventing collapse into infinite density. Black holes might instead become quantum bounces, where matter rebounds into new universes. Even more mind-bending, time itself could be quantized. Just as a movie's smooth motion hides individual frames, what we perceive as continuous time might be a cascade of discrete moments, each a click of the universe's underlying clock. Experiments hunting for this granularity are already underway. Some pulsar observations hint at spacetime behaving like a fine mist when probed by ultra-high-energy gamma rays, as if light occasionally stumbles over the vacuum's hidden texture. Critics argue loop quantum gravity is untested, lacking string theory's mathematical elegance. Yet its minimalist approach, no extra dimensions, no unobserved particles, appeals to those who crave a universe built from spacetime alone. Whether it's the final answer or just another stepping stone, one thing's clear. If loop quantum gravity is right, the vacuum isn't just mysterious. It's the universe's deepest architectural blueprint, whispering secrets about how reality is stitched together at the smallest scales imaginable. What if everything we see, every star, every atom, even the vacuum itself, is nothing more than a shadow, a cosmic mirage projected from the edges of reality. This isn't science fiction. It's the holographic principle, a theory so radical it suggests our three-dimensional universe might be a vast illusion. Its true nature written in two-dimensional code on the fabric of spacetime itself. At the heart of this idea lies a startling twist. The quantum vacuum, that seething ocean of energy we've been exploring, could be nothing more than a hologram, a projection from a distant, unseen surface. The story begins with black holes, those gravitational monsters that twist spacetime into knots. In the 1970s, physicist Jacob Bekenstein made a bizarre discovery. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume as you'd expect, but to its surface area. It's as if all the data about what's inside a black hole gets compressed onto its event horizon, like a cosmic hard drive. Decades later, string theorist Leonard Susskind took this further, proposing that the entire universe might work the same way. Just as a hologram stores a 3D image on a 2D film, spacetime itself could be a projection from a boundary we can't see. Here's where the vacuum gets weird. If the holographic principle is true, then every fluctuation in the quantum foam, every virtual particle, every ripple of zero-point energy isn't truly happening inside space. Instead, it's being computed on some distant surface like pixels on a screen, and then rendered into the 3D illusion we experience. Think of it like watching a movie. The images seem deep and real, but they're actually flat patterns of light on a theater wall. The vacuum, in this view, isn't the ultimate foundation of reality. It's the output of a deeper process, a cosmic algorithm running on the universe's edge. But how could this possibly work? One clue comes from quantum entanglement, that spooky connection between particles we discussed earlier. Entanglement seems to thread space with invisible links, tying distant points together in ways that defy classical geometry. Some theorists argue these threads are the stitches of the hologram, weaving the illusion of a 3D vacuum from 2D data. It's as if spacetime is a tapestry, and the deeper you look, the more you realize it's just tangled strings of information. The implications are staggering. If the vacuum is a hologram, then the infinities plaguing quantum field theory, those nonsensical numbers we keep renormalizing away, might just be glitches in the projection. The true calculations could be happening on a simpler 2D surface where infinity never appears. Even dark energy, that enigmatic force accelerating the universe's expansion, might be a side effect of the hologram's encoding, like compression artifacts in a digital image. Of course, not everyone's convinced. Critics point out that the holographic principle remains largely theoretical, with no direct experimental proof. Yet tantalizing hints emerge from unexpected places. Take the Fermi paradox, the eerie silence of the cosmos despite its seeming potential for life. If the universe is a hologram, its information capacity isn't infinite. There might simply be less space in the code than we think, limiting the number of civilizations that can arise. Whether the holographic principle holds or not, it forces us to confront a humbling possibility. The quantum vacuum, with all its complexity, might just be the surface of something far stranger. So the next time you gaze at the night sky, ask yourself, are you looking into the depths of reality or just reading the universe's shadow play? Could the quantum vacuum, that bubbling sea of energy, hold the secret to shortcuts through spacetime? Buried within its microscopic chaos, some physicists suspect an even wilder possibility. Wormholes, those cosmic tunnels beloved by science fiction, might flicker in and out of existence at scales so small they make atoms look like planets. This isn't just fantasy. The math suggests that at the Planck length, a millionth of a billionth of a billionth the width of an atom, quantum foam churns so violently that spacetime itself becomes a frothing mess of tunnels and bridges. Tiny wormholes could be popping into existence and vanishing trillions of times per second, woven from the vacuum's own instability. But here's the tantalizing twist. What if we could catch one? Wormholes, according to Einstein's equations, are theoretically possible, but they'd require something called exotic matter to hold them open, a substance with negative energy that pushes space-time outward instead of pulling it inward. And guess what? The quantum vacuum might already be manufacturing it. Virtual particles, those ghostly pairs that flash in and out of existence, sometimes behave as if they carry negative energy. Casimir plates, as we've seen, demonstrate this by creating a region of negative energy density between them. Could a sufficiently advanced civilization manipulate these vacuum fluctuations to stabilize a wormhole, turning a fleeting quantum quirk into a galactic freeway? The obstacles are staggering. Planck-scale wormholes would be unimaginably small, far tinier than an electron, and stabilizing one would require energies beyond anything we can produce. Even if we could, keeping a wormhole open long enough to traverse it might demand more negative energy than exists in the observable universe. And then there's the causality problem. Wormholes could create time loops, allowing information to travel back in time and shattering our understanding of cause and effect. Yet the idea refuses to die. Some theorists speculate that certain configurations of dark energy, the mysterious force accelerating the universe's expansion, might naturally stabilize wormholes on cosmic scales. Others suggest that black holes, those space-time warping behemoths, might already be connected by hidden bridges, with their singularities acting as gateways. If true, the vacuum wouldn't just be a chaotic foam, it'd be a labyrinth of untapped shortcuts waiting for us to crack the code. For now, these wormholes remain ghosts in the equations. But the mere possibility forces us to ask, is the quantum vacuum just the static backdrop of reality, or is it the universe's ultimate construction site, constantly building and demolishing the fabric of space-time itself? One of the greatest enigmas in cosmology begins with a simple question: what lit the fuse for the universe's explosive birth? The leading answer lies buried in the quantum vacuum's deepest layers. According to inflation theory, a fraction of a second after the Big Bang, space didn't just expand, it erupted, swelling faster than light itself, the force behind this cosmic hyperdrive. A hypothetical field called the inflaton, thought to have borrowed its staggering energy from the vacuum's own cryptic reserves. Picture a snowball rolling downhill, gathering mass and momentum with every turn. Now imagine that snowball is space-time, and the hill is a slope of vacuum energy. Inflation suggests the early universe hit a quantum jackpot, an unstable patch of vacuum where the inflaton field got stuck in a high-energy state, like a ball balanced on a ridge. As this field slowly rolled toward its lowest energy level, it released pent-up vacuum energy that inflated space exponentially, stretching a region smaller than a proton to cosmic proportions in less than a trillionth of a second. The evidence, our universe's eerie uniformity. Look at the cosmic microwave background, the afterglow of the Big Bang, and you'll see temperature fluctuations no greater than 1 part in 100,000. Without inflation, regions now billions of light-years apart could never have reached equilibrium. Yet inflation's rapid stretch would have ironed out cosmic wrinkles, leaving behind the smooth, flat universe we observe. Even the seeds of galaxies might owe their existence to quantum vacuum fluctuations, magnified to cosmic scales during inflation's runaway expansion. But here's the controversy: inflation is a theory in crisis. While it elegantly solves multiple cosmological puzzles, it makes few testable predictions. Worse, some critics argue it's become a theory of anything, flexible enough to explain contradictory observations by tweaking parameters. Nobel laureate Roger Penrose has called it wishful thinking, while others point out that the inflaton field remains purely hypothetical with no direct detection. The verdict may lie in upcoming experiments. Next-generation telescopes like the Simons Observatory and Lightbird are hunting for primordial gravitational waves, ripples in spacetime from inflation's violent throes. If detected, their patterns could reveal the inflaton's energy scale, even hinting at quantum gravity's fingerprints. Others propose scrutinizing the cosmic microwave background for anomalies, circular patterns that might betray collisions with other bubble universes, if ours is just one inflated pocket in a multiverse. The stakes couldn't be higher. If inflation is confirmed, it would mean the vacuum didn't just shape the universe, it birthed it, turning a quantum whisper into a cosmic roar. If disproven, we're back to square one, forced to rethink the universe's first moments. Either way, the answer lies in the vacuum's shadowy depths, where the line between nothing and everything blurs beyond recognition. So was inflation a fleeting quantum fluctuation or the universe's greatest magic trick? The vacuum holds the secret, and we're closer than ever to hearing its whispered reply. Consciousness might be the most intimate mystery we'll ever confront, the silent theater where reality unfolds, the voice in your head reading these words right now. But what if that voice isn't just the product of neurons firing? What if it's whispering in harmony with the quantum vacuum itself? This isn't mainstream science yet, but a provocative fringe idea suggests that the very fabric of our awareness could be entangled with the void's hidden depths. At the heart of this radical theory lies a tiny structure inside your brain's neurons, microtubules. These cylindrical proteins, far smaller than synapses, were long thought to be mere cellular scaffolding. But in the 90s, physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff proposed something extraordinary. They argued that microtubules might harness quantum vibrations, tiny oscillations in the vacuum's energy field, to orchestrate consciousness. In their model, dubbed orchestrated objective reduction, these vibrations collapse into coherent states, creating moments of awareness like notes in a cosmic symphony. The implications are staggering. If true, it would mean every thought, every flicker of perception is a dance with the quantum vacuum's seething energy. When you smell coffee or feel joy, microtubules could be tapping into the same primordial fluctuations that birth virtual particles in deep space. Even more controversially, this theory suggests consciousness might not be confined to the brain. It could be a fundamental feature of the universe, woven into the vacuum's fabric like gravity or light. Skeptics pounce hard. The brain is warm, wet, and noisy, a hostile environment for delicate quantum states, which usually require near absolute zero temperatures to avoid decoherence. Yet recent experiments hint at surprises. Some studies show microtubules vibrating at frequencies that align with Penrose's predictions, while others suggest certain anesthetics disrupt these quantum vibrations precisely when consciousness fades. Then there's the Libet experiments, where brain activity precedes conscious decisions by milliseconds, a gap some interpret as quantum processing time. The debate rages, but the deeper question lingers. If the vacuum's energy can influence matter on cosmic scales, why not on synaptic ones? After all, photosynthesis, a process vital to life, relies on quantum coherence in plant cells. Could evolution have stumbled upon similar tricks inside our skulls? The idea teeters between genius and madness, but that's where breakthroughs often hide. Perhaps the most poetic possibility is this: if consciousness emerges from the vacuum, then self-awareness isn't just happening in the universe, it's the universe becoming aware of itself. The void wouldn't be empty, it'd be alive, humming with the same unseen rhythms that shape our innermost thoughts. Whether proven or debunked, this theory forces us to confront a hauntingly beautiful notion that the line between mind and cosmos might be far thinner than we ever dared to dream. Conventional wisdom tells us the vacuum of space is the coldest place imaginable, a desolate freeze where temperatures plunge near absolute zero. But the quantum vacuum defies intuition yet again. Far from being a lifeless chill, it crackles with a hidden heat, a thermal signature that only appears under extreme conditions. This revelation comes from two of physics' most startling phenomena, the Unruh Effect and Hawking radiation, where motion and gravity conjure warmth from pure nothingness. Picture an astronaut accelerating through the void at nearly light speed. To an outside observer, they're coasting through an icy abyss, but for the astronaut, something extraordinary happens. The vacuum around them begins to glow with heat, as if space itself were a cosmic sauna. This is the Unruh effect in action, where acceleration transforms the vacuum's flickering quantum fields into a bath of warm particles. The faster you accelerate, the hotter the glow becomes, like rubbing your hands together in winter, except here, motion heats the very fabric of reality. What's truly mind-bending is what this implies about temperature itself. We think of it as absolute, an objective measure of molecular motion, but the Unruh effect shows it's relative, a matter of perspective tied to motion through the quantum vacuum. A thermometer at rest might read near zero, while one accelerating violently could register hundreds of degrees. This isn't an illusion, the particles are real, measurable. Space isn't just cold, it's both cold and hot depending on how you move through it. Now consider black holes where gravity plays the same role as acceleration. At the event horizon, the gravitational pull is so fierce that virtual particle pairs usually annihilating instantly get torn apart. One particle falls into the black hole while the other escapes as radiation, carrying away energy. This is Hawking radiation, and it means black holes aren't truly black. They glow, slowly evaporating over eons with a temperature inversely proportional to their size. A tiny black hole could radiate fiercely, while a supermassive one would emit a faint, icy whisper. Here's the thermodynamic twist. Both effects suggest the vacuum isn't passive. It's a dynamic medium where energy and motion rewrite the rules of heat and cold. If an accelerating observer sees particles where a stationary one sees none, whose perspective is real, the answer forces us to confront a radical idea. Temperature might not be a property of space alone, but of how we interact with it. Could this duality hint at deeper laws? Some theorists speculate that the Unruh and Hawking effects are two sides of the same coin, a unified principle linking acceleration, gravity, and quantum fluctuations. Others wonder if this thermal ambiguity is a clue about spacetime's underlying structure, like pixels in a cosmic display adjusting their brightness based on the observer's state. One thing's certain, the quantum vacuum's temperature isn't just a curiosity, it's a window into relativity's and thermodynamics' hidden marriage. So the next time you gaze at the night sky, remember, the void isn't cold or hot. It's both and neither. It all depends on how fast you're willing to go. Time flows forward, inexorable, irreversible, like sand through an hourglass, yet nothing in the fundamental laws of physics explains why. The equations work just as well backward as forward, so why does time have an arrow at all? The answer might lie in the quantum vacuum's most overlooked property, its entropy. Picture a shattered glass reassembling itself, smoke gathering back into a cigarette, or an explosion reversing into a firework. These everyday impossibilities reveal the universe's greatest asymmetry. Entropy, the measure of disorder, always increases. But entropy needs a starting point, a state of pristine order to unravel from. That starting point, some theorists argue, might have been etched into the fabric of the early universe by the vacuum itself. Right after the Big Bang, the cosmos was unfathomably uniform, a near-perfect soup of energy with staggeringly low entropy. This improbable order set the stage for everything to come. As the universe expanded, gravity amplified tiny quantum fluctuations left over from the vacuum's primordial hum, sculpting galaxies from chaos. But here's the twist, those fluctuations might have been time's hidden architect. Consider a deck of cards fresh from the factory, mint condition, all suits in order. Shuffle it once and the disorder grows. The vacuum's early state was like that pristine deck, and its quantum jitters were the first shuffle. Once those fluctuations tipped the scales, entropy had a direction to flow, like a single domino nudged, beginning an irreversible cascade. The stakes of this idea are cosmic. If the vacuum's low entropy state truly set time's arrow, it implies something astonishing. The flow of time isn't just a property of matter or energy, but of emptiness itself. The void isn't passive, it's a silent conductor orchestrating the universe's one-way march from order to chaos. Yet mysteries remain. Why was the early vacuum so ordered? Some suggest inflation, that explosive expansion of spacetime ironed out irregularities, creating a blank slate. Others propose more exotic answers, like the vacuum being trapped in a rare low-entropy configuration by sheer statistical fluke. A few even speculate about a deeper connection between quantum entanglement and entropy, where the vacuum's hidden correlations act as time's invisible gears. Whatever the answer, the implications are dizzying. If the vacuum holds time's secret, then every second passing is an echo of the void's first whisper, a reminder that even nothingness pulses with the rhythm of creation. Supersymmetry offers one of the most elegant solutions to physics' biggest puzzles, if only nature would cooperate. The theory suggests every known particle has a hidden twin, a superpartner lurking in the vacuum's shadowy depths. Electrons would be paired with selectrons, quarks with squarks, photons with photinos, each one a mirror image differing only in spin. These particles aren't just whimsical additions. They could solve the Higgs mass problem, unify forces, even account for dark matter. Yet after decades of searching, the Large Hadron Collider has found no trace of them. So where are they? The math behind supersymmetry is undeniably beautiful. It smooths out quantum field theory's jagged edges, balancing equations so perfectly that infinities cancel like magic. Without supersymmetry, the Higgs boson's mass should be inflated to impossible scales by quantum corrections, like a snowball rolling downhill, gathering virtual particles until it's planetary in size. But introduce superpartners and their contributions precisely offset this runaway growth, keeping the Higgs featherlight. The vacuum, in this view, isn't just chaotic. It's a meticulously tuned scale where every fluctuation has its counterweight. But the cosmos loves throwing curveballs. Despite the LHC's proton-smashing fury, no squarks or photinos have appeared in the wreckage. This absence forces a reckoning. Is supersymmetry wrong, or are we looking in the wrong way? Some theorists argue superpartners might be heavier than expected, beyond the LHC's current energy reach. Others propose they're nearly invisible, interacting so weakly they slip through detectors like ghosts. There's even a wild card. What if supersymmetry isn't exact? Perhaps superpartners are fractured mirrors of their twins, differing just enough to evade detection while still preserving the theory's mathematical grace. The stakes are cosmic. If supersymmetry is real, the vacuum could be teeming with these shadow particles, their collective mass shaping galaxies as dark matter. If not, physicists face a brutal choice: abandon decades of elegant theory or accept that nature's rulebook is messier than we hoped. For now, supersymmetry lingers in limbo, not dead, but waiting for technology to catch up to its brilliance. The next generation of colliders may hold the answer, probing energies where these vacuum dwellers might finally step into the light. Until then, the hunt continues, not just for particles, but for the very soul of theoretical physics. Black holes already defy logic spacetime, warped so severely that even light can't escape. But what happens at the very edge, where the vacuum brushes against a black hole's event horizon? Prepare for one of physics' fiercest battles, where relativity and quantum mechanics clash over a nightmarish possibility that the void itself might ignite into an inferno. This is the AMP's firewall paradox, a cosmic showdown that threatens to rewrite our understanding of reality's most extreme frontier. The drama begins with Hawking radiation. As we've seen, quantum fluctuations near a black hole's horizon create particle pairs. One falls in, the other escapes, slowly evaporating the black hole over eons. But here's the catch: those escaping particles must be entangled with their doomed twins to preserve quantum information. Otherwise, the universe violates a sacred rule: information can't be destroyed. Yet in the 1990s, physicists Ahmed Olmary, Donald Marolf, Joe Pulczynski, and James Sully spotted a fatal flaw. If the escaping particle remains entangled with its fallen partner and with earlier radiation as quantum theory demands, it creates a chain of forbidden double entanglement. The only escape, a firewall, a blistering wall of energy at the horizon that vaporizes anything crossing it, severing the entanglement and saving quantum consistency. Picture this: instead of drifting peacefully into a black hole, you'd hit a barrier hotter than a supernova, a Planck-scale maelstrom where the vacuum itself turns ferocious. Relativity, however, screams foul. Einstein's equations insist the horizon should be uneventful, a smooth patch of spacetime where free-falling observers feel nothing unusual. Hence the paradox: quantum mechanics demands a firewall to protect information. Relativity forbids it to preserve the equivalence principle. One theory must break, and nobody knows which. The stakes: everything. If firewalls exist, black holes aren't the gentle traps we imagined, they're cosmic incinerators. If they don't, quantum mechanics might need radical revision. Some theorists propose loopholes, fuzzballs, where horizons are replaced by tangled quantum strings, or equals conjectures where wormholes secretly shuttle information. Others suggest the paradox reveals a deeper truth, that spacetime itself is emergent, stitched together by quantum entanglement, and the firewall marks where that stitching phrase. For now, the AMPS paradox stands as physics' ultimate tug-of-war, a duel between two titanic theories with the quantum vacuum caught in the crossfire. Whatever the answer, one thing's clear: near a black hole, emptiness is anything but peaceful. What if the quantum vacuum isn't just a chaotic sea of energy, but a tapestry with hidden folds, wrinkles in spacetime itself left over from the universe's fiery birth? This is the tantalizing possibility behind vacuum topology, where emptiness might be knotted with defects so strange they could rewrite the cosmos. Picture the early universe cooling from its primordial inferno, like molten metal hardening into steel. As it expanded and cooled, theorists suggest the vacuum's underlying structure might have frozen imperfectly, leaving behind cosmic scars, thread-like cracks in reality called cosmic strings, or isolated poles of magnetic charge known as monopoles. These wouldn't be mere anomalies, they'd be fossils of creation, carrying secrets from the first moments after the Big Bang. Take cosmic strings, hypothetical filaments thinner than an atom yet stretching across galaxies. According to some grand unified theories, these defects could have formed as the universe underwent phase transitions, much like ice crystals forming in water, but on a cosmic scale. A single cosmic string, though unimaginably thin, might weigh more than a mountain range packed into every mile, warping spacetime around it like a taut wire bending a sheet. If they exist, these strings could create double images of distant galaxies as their gravity bends light, or even produce ripples in spacetime gravitational waves as they vibrate or snap. The echoes of such events might already be hiding in data from observatories like LIGO, waiting to be uncovered. Then there are magnetic monopoles, particles with only a north or south pole, unlike any magnet we've ever seen. Their existence was predicted by physicist Paul Dirac, who showed that if just one monopole lurked in the cosmos, it would explain why electric charge comes in neat, discrete units. But despite decades of searching, from deep underground labs to cosmic ray detectors, monopoles remain missing. Some theories suggest inflation, that explosive expansion of the early universe might have diluted them to near non-existence, scattering them so thinly that finding one would be like spotting a single grain of sand in a desert. Others propose they're bound up in higher dimensions, invisible to our current tools. The hunt for these vacuum defects isn't just academic. If cosmic strings exist, they could be the universe's original gravitational wave generators, offering a window into energies far beyond what colliders can reach. Monopoles, meanwhile, might hold the key to unifying the fundamental forces, bridging the gap between quantum mechanics and gravity. Even their absence tells a story, hinting that our universe's vacuum froze into its current state with unusual smoothness, avoiding the defects that other possible universes might harbor. So is the vacuum knotted with hidden imperfections, or is it flawlessly symmetrical? The answer could reveal whether our cosmos is a rare masterpiece or just one of countless textures in an even grander cosmic quilt. Either way, these phantom structures remind us that emptiness is never truly empty. It's a living record of how reality stitched itself together. At the heart of quantum mechanics lies a paradox so baffling it haunted even Einstein. Why do we perceive a single, concrete reality when the math insists every possibility coexists in ghostly superposition until observed? The answer might not lie in human consciousness or hidden variables, but in the quantum vacuum itself. This is the frontier of quantum Darwinism, a radical idea suggesting the vacuum isn't just a passive backdrop, it's an active participant, sculpting the chaotic quantum fog into the stable world we experience. Picture an electron orbiting an atom. According to quantum theory, until measured, it doesn't occupy a fixed position. It exists as a smear of probabilities, a blur of could-be states. Yet when we look, we always find it in one place. Decoherence theory explains this collapse as environmental noise, air molecules, photons, even cosmic rays constantly bumping into quantum systems, stripping away their ambiguity. But here's the twist. The quantum vacuum's fluctuations could be the first and most universal of these interactions, the primordial sieve that filters quantum weirdness into classical certainty. Think of the vacuum as a cosmic bouncer at reality's nightclub. Virtual particle pairs constantly popping in and out act like tiny disturbances, measuring quantum systems by interacting with them. Over time, only the most robust quantum states, those least disrupted by these fluctuations, survive to become what we perceive as objective reality. The rest vanish into the void like whispers drowned out by static. In this view, the vacuum doesn't just allow reality to exist, it actively selects which versions get to stick around. The implications are staggering. If quantum Darwinism holds, the vacuum isn't just hosting the universe, it's curating it. Consider Schrödinger's infamous cat, simultaneously alive and dead in its box. The vacuum's ceaseless interactions might explain why we never see such superpositions at human scales. Large objects with trillions of particles are constantly bombarded by vacuum fluctuations, forcing their quantum states to pick a side almost instantly. A single electron might linger in superposition for microseconds, but a cat or a car or a planet collapses too fast for us to catch it in the act. This raises a profound question. Is the classical world we see just the vacuum's favorite set of quantum states, the ones resilient enough to endure its relentless churn? Some theorists take this further, suggesting the vacuum's preferences might even shape the laws of physics themselves. Just as Darwinian evolution favors traits that enhance survival, quantum Darwinism could mean our universe's constants, the speed of light, the strength of gravity, are the fittest configurations, stable against the vacuum's disruptive whispers. Yet mysteries remain. Why do certain states win over others? Is there a deeper principle guiding the vacuum's selections, or is it pure randomness? Experiments with increasingly isolated quantum systems like ultra-cold atoms shielded from all noise except vacuum fluctuations might soon test these ideas. If the vacuum truly is reality's silent editor, then every rock, star, and living creature is the product of an ancient, invisible negotiation between quantum possibility and the void's relentless winnowing. So next time you touch a table or watch a sunset, remember, what you perceive as solid and certain might just be the quantum vacuum's grandest illusion, the versions of reality that shouted loudest over the noise of nothingness. Silence isn't what you think it is, not in the quantum vacuum. Amid its seething energy, physicists are chasing an idea so strange it bends the rules of perception. the vacuum might hum, not with audible sound, but with vibrations so subtle they could rewrite our understanding of gravity itself. These hypothetical ripples, called phonons, aren't ordinary sound waves. They're collective vibrations in exotic materials like ultra-cold Bose-Einstein condensates or crystalline structures where atoms move in eerie lockstep. And here's the wild part: these phonons could be the key to simulating quantum gravity in a lab, turning abstract equations into something we can almost hear. Picture a frozen lake on a windless day. At first glance, it's perfectly still, but peer closer, and you'll see tiny vibrations skittering across its surface, the ice's atomic lattice humming with imperceptible energy. In certain states of matter, like superfluid helium or synthetic quantum materials, the vacuum's fluctuations can trigger analogous vibrations. These phonons behave like sound waves, but with a quantum twist. They're discrete packets of energy, echoes of the vacuum's hidden structure. Theorists suggest that if we could precisely control these vibrations, they might mimic the behavior of gravitons, the hypothetical particles thought to carry gravity in quantum field theory. It's like using ripples in a pond to model ocean tides, scaling cosmic mysteries down to tabletop experiments. The implications are revolutionary. Quantum gravity has long been physics' white whale, a theory that unifies Einstein's relativity with quantum mechanics. But gravity is laughably weak compared to other forces, making it nearly impossible to study at quantum scales. Enter analog gravity, a clever workaround where researchers recreate conditions akin to black holes or the early universe in controlled settings. By tuning phonons in exotic materials, scientists could simulate how gravity interacts with quantum fields, watching as artificial event horizons bend these sound waves, just as real space-time bends light. Already, experiments with superfluid helium have reported phonon behavior resembling Hawking radiation. The thermal glow predicted near black holes. It's as if the vacuum's whispers are teaching us to speak the language of the cosmos. But why sound? The answer lies in symmetry. Phonons and gravitons both arise from collective excitations in their respective media, or whether a crystal lattice or space-time itself. Mathematically, their equations share striking parallels, hinting at a deeper connection between vibrations in matter and the fabric of the universe. Some theorists even speculate that space-time might emerge from a more fundamental network of interactions, like a 3D hologram projected from quantum entanglement. If phonons in a lab can effectively trick reality into behaving like curved space-time, it would suggest gravity isn't primary, it's a side effect of something far stranger. Of course, challenges loom. Phonon simulations are crude approximations, and translating their lessons to real quantum gravity requires leaps of imagination. Critics argue these experiments are little more than metaphors, with no guarantee the universe plays by the same rules as a vat of ultra-cold atoms. Yet even skeptics admit the audacity of the idea that the vacuum's sound, a vibration in what we once called nothingness, might hold the key to the universe's deepest secret. So the next time you hear silence, remember, it might just be the hum of space-time itself, waiting for us to listen closely enough. The cosmic lottery we call home might not be as special as we think, just one lucky ticket in an infinite sea of losing stubs. According to the multiverse theory, our universe is just right vacuum energy, calibrated so precisely that galaxies could form and life could emerge, could be a statistical fluke. The idea springs from eternal inflation, a mind-bending twist on the Big Bang where the universe isn't just expanding, but birthing new universes in a never-ending cascade. Picture a boiling pot of water, bubbles forming and drifting apart. Now imagine each bubble is an entire cosmos, each with its own random vacuum energy, its own laws of physics. Some so unstable they collapse instantly, others so empty nothing ever forms. Our universe, just one bubble in the froth, its delicate balance not designed but drawn from an infinite deck of possibilities. This isn't just speculative fiction. The math of inflation suggests it's possible, even likely. When quantum fluctuations in the early vacuum triggered inflationary expansion, some regions might have tunneled into lower energy states, pinching off into separate universes. Each transition would lock in a new vacuum energy, a new set of constants. In most, the numbers would spell doom: vacuum energy so high atoms never bond, or so low gravity crushes everything into sludge. But in a vanishingly rare few, like ours, the numbers line up just right for stars, planets, and curious minds to ponder why they exist at all. The implications are humbling. If true, our universe's fine-tuning isn't a miracle, it's inevitability by brute force probability. Like shuffling a deck of cards until by chance you deal a perfect royal flush. Critics argue this is a cop-out, a way to dodge the why behind our universe's improbable luck. Even the term multiverse raises eyebrows. If other universes are permanently cut off from ours, how could we ever test their existence? Yet clues might lurk in the cosmic microwave background, where collisions with neighboring bubble universes could leave faint, circular bruises in the sky. Others suggest that if our vacuum is metastable, perched precariously above a lower energy state, its eventual decay could hint at deeper layers of reality. The multiverse idea forces a radical shift in perspective. What we call the laws of physics might just be local bylaws, quirks of our cosmic neighborhood. Elsewhere, gravity could repel, light might crawl, and time could flow backward. And the quantum vacuum, not a universal constant but a chameleon, shifting its nature with each new bubble. Whether this vision is profound or preposterous, one thing's clear. If the multiverse is real, then the void we call home is far stranger and far less lonely than we ever imagined. Magnets are supposed to come in pairs, a north pole inseparable from its south, but the quantum vacuum might be hiding a rebellious exception. Lurking in the equations of grand unified theories is a prediction so bold it could rewrite electromagnetism. Magnetic monopoles, solitary north or south poles unshackled from their counterparts. These phantom particles aren't just missing puzzle pieces. They're cosmic fugitives whose absence has physicists questioning the very foundations of how forces unite. The story begins with Paul Dirac, who proved in the 1930s that if even one monopole exists anywhere in the universe, it would explain why electric charge comes in neat, indivisible units. But the real excitement came decades later when grand unified theories, ambitious frameworks aiming to merge electromagnetism with the strong and weak nuclear forces, demanded their existence. These theories suggest that in the searing heat of the early universe, the vacuum's energy field underwent phase transitions like water freezing into ice. Just as cracks form in freezing lakes, these transitions could have spawned topological defects, knots in spacetime where magnetic charge concentrates into isolated poles. The numbers are staggering. A single grand unification scale monopole would weigh as much as a bacterium packed into a space smaller than a proton, carrying magnetic charge trillions of times stronger than anything found in nature today. If they're out there, they'd be cosmic bulldozers ionizing matter in their path, leaving trails of destruction across galaxies. Yet despite decades of hunting with detectors buried deep underground, scoured Antarctic ice, and even repurposed particle colliders, not one definitive monopole has been found. This isn't just a case of bad luck. The absence cuts to the heart of grand unified theories, forcing physicists into uncomfortable corners. Some propose that inflation, the universe's exponential expansion, diluted monopoles to near non-existence, scattering them so thinly that finding one would require sifting through a volume of space larger than our galaxy. Others suggest monopoles are bound inside higher dimensions or hidden within cosmic strings, those hypothetical space-time cracks we discussed earlier. A more radical faction argues that monopoles do exist but have been masquerading as something else, perhaps certain dark matter candidates or even primordial black holes. The quest hasn't been fruitless. In 2014, a team at the South Pole's ice cube detector observed an event with monopole-like energy signatures, setting the physics world abuzz until follow-ups ruled it out. Meanwhile, labs like the Large Hadron Collider are hunting for fractional monopoles, where emergent phenomena in exotic materials mimic their behavior. It's like searching for a shadow instead of the object itself, hoping the imitation will reveal the real thing's secrets. The stakes go beyond particle physics. If monopoles exist, they'd be relics of the universe's first trillionth of a second, offering a direct window into energy so high no collider could ever reach them. Their structure might encode how forces fractured from their primordial unity, like frozen snapshots of cosmic adolescence. But if they're truly absent, grand unified theories might need radical surgery or abandonment altogether. So is the vacuum secretly hoarding these magnetic rebels, or are we chasing a cosmic mirage? The answer could determine whether our universe's forces are threads of a single tapestry or strands we've mistakenly tied together. Either way, the hunt continues because in the quantum void, even absence speaks volumes. The Higgs field is often called the universe's molasses, a cosmic syrup that slows particles down, giving them the illusion of mass. But there's one particle that refuses to play by the rules, the neutrino. These ghostly particles streaming through your body by the trillions every second weigh almost nothing, 1,000,000 times lighter than an electron. How can the same vacuum that makes a top quark feel like a lead brick leave neutrinos practically weightless? The answer might lie in one of physics' most daring sleights of hand, the seesaw mechanism, and it hints that the vacuum could be hiding dimensions far beyond our perception. Start with the basics. When most particles like electrons or quarks move through the Higgs field, they interact strongly, like wading through deep water. The more they push against this invisible molasses, the heavier they become. But neutrinos barely interact at all. For decades, physicists assumed they were massless until experiments in the late 1990s caught them oscillating, changing flavors mid-flight, a trick only possible if they have some tiny mass. The discovery shattered the standard model's neat symmetry, forcing a scramble for explanations. Enter the seesaw. Picture a playground teeter-totter. One side is almost touching the ground, the other impossibly high. Now imagine the low side is the neutrino we know ridiculously light, while the high side is a hypothetical, ultra-heavy neutrino, tipping the scales at energies 1,000,000,000,000 times beyond the Large Hadron Collider's reach. The seesaw mechanism proposes these two particles are linked through the vacuum's hidden geometry. The heavier one tugs downward, making its sibling almost weightless by comparison. If true, it means our universe's neutrinos are just the feather-light echoes of monsters lurking in realms we can't yet probe. But where could these heavy neutrinos hide? Some theories suggest extra dimensions, tiny, curled-up folds in spacetime where particles gain mass by leaking into higher realms. Others propose a grand unified theory where neutrinos acquire mass not just from the Higgs, but from a completely separate field that permeates the vacuum. The wildest idea, that neutrinos are Majorana particles, entities that are their own antimatter twins, which would mean they could gain mass by interacting with themselves through quantum loops in the vacuum, no Higgs required. The stakes are cosmic. If the seesaw mechanism is real, it would imply the vacuum is far richer than we imagined, with particles oscillating between dimensions or whispering to unseen partners. It could also explain why matter dominates over antimatter in the universe, a puzzle tied to neutrinos' bizarre behavior. Experiments like the Deep Underground Neutrino Experiment (DUNE) are hunting for clues, while theorists race to reconcile these ideas with dark matter and quantum gravity. For now, the neutrino's featherweight mass remains a whisper in the void, a quiet challenge to everything we think we know about the vacuum's power to shape reality. And if history's any guide, wherever neutrinos defy explanation, a revolution in physics usually follows. Deep in the cosmic static, buried beneath the hum of galaxies and the afterglow of the Big Bang, there might be whispers from the very first moments of existence, ripples in space-time so ancient they predate light itself. These are primordial gravitational waves, and if they exist, they could carry the faintest imprints of the quantum vacuum's furious activity during inflation, that explosive expansion of the universe's infancy. Think of it like an echo trapped in a canyon for billions of years, slowly fading but never vanishing. Only here the canyon is space-time and the echo isn't sound, it's the vibration of the vacuum itself, frozen into the fabric of reality. The story begins with inflation's unimaginable energies. As the universe ballooned from smaller than an atom to cosmic proportions in a fraction of a second, quantum fluctuations in the vacuum, those fleeting particles and fields we've explored, got stretched to macroscopic scales. Some became the seeds of galaxies, others, theorists suspect, might have agitated spacetime so violently they spawned gravitational waves. Unlike the waves we detect from colliding black holes today, these primordial ripples would be absurdly long light years in wavelength and impossibly faint, their signals drowned out by the universe's later chaos. But if we could catch them, they'd be a time machine to the universe's first trillionth of a second, revealing how the vacuum behaved when reality was still taking shape. The hunt hinges on a cosmic fossil, the cosmic microwave background, or CMB. This afterglow of the Big Bang, imprinted when the universe was just 380,000 years old, might bear subtle swirls called B-mode polarization, patterns etched by gravitational waves passing through the infant cosmos. In 2014, the BICEP 2 team thought they'd spotted these swirls, a discovery that sent shockwaves through physics until interstellar dust muddied the signal. But next-generation experiments like the Lightbird satellite and the Simons Observatory are upgrading the search with exquisitely sensitive detectors, poised to sift the CMB's faint whispers from the noise of the universe. Yet the real prize lies beyond even the CMB. Some theorists dream of a future where we detect primordial waves directly, using observatories like the proposed Big Bang Observer, a space-based array of lasers sensitive enough to catch spacetime's oldest tremors. The challenge: these waves would stretch and compress Earth by less than an atom's width over millions of miles. It's like trying to hear a pin drop on the other side of a hurricane. But if we succeed, the payoff would be staggering. Confirmation that the vacuum's quantum jitters not only seeded galaxies but literally shook spacetime into existence. The implications spiral outward. If primordial waves match predictions, they'd confirm inflation's most exotic models, some of which tie the vacuum's energy to string theory or multiverses. A null result, though, could mean inflation wasn't as violent as we thought, or that we're missing something fundamental about how quantum fluctuations interact with gravity. Either way, these echoes aren't just relics, they're a mirror held up to the vacuum's wild youth, showing us how chaos crystallized into cosmos. So while we wait for detectors to tune in, remember, the universe's first seconds might still be ringing in the void if only we learn how to listen. Teleportation isn't just for sci-fi anymore thanks to the quantum vacuum. Scientists have already pulled off the impossible, teleporting information between particles separated by miles. This isn't magic, it's the eerie power of entanglement, where particles become so deeply linked that manipulating one instantly affects its partner, no matter the distance. And here's the twist: the vacuum itself might be the invisible highway making it all possible. Take the groundbreaking experiments in China and Austria, where researchers teleported the quantum states of photons across cities, even between ground stations and satellites. They didn't send physical particles, just the information locked inside them, using entangled pairs as a relay. Imagine two dice spinning in perfect sync, one in Vienna and the other in Beijing. Roll one and the other instantly lands matching, except these dice are photons, and their synchronized behavior bypasses the speed of light, the secret. The vacuum's entanglement networks, where particles share a hidden connection that doesn't rely on traditional signals. But how does the vacuum play into this? Every entangled pair is born from the same quantum fluctuation, a flicker in the vacuum's energy field. When two particles emerge from this void, their properties are intertwined at a fundamental level, like reflections in a mirror. The vacuum doesn't just host this entanglement, it preserves it, acting as a silent mediator that keeps the particles' connection intact, even as they're hurled to opposite sides of the planet. Some theorists suggest the vacuum's zero-point fluctuations, those ghostly particles popping in and out of existence, might even stabilize the entanglement, preventing it from crumbling under environmental noise. The implications are staggering. If we could scale this up, the vacuum could become the backbone of a quantum internet, a network where information leaps between nodes instantaneously, secured by the laws of quantum mechanics. No hackers, no lag, just flawless teleportation powered by the void's hidden architecture. Already, labs are testing quantum repeaters, devices that extend entanglements range by stitching together segments of the vacuum's quantum fabric. Yet mysteries remain. Why does entanglement survive the vacuum's chaos? Could we ever teleport more complex information, or even, as wild as it sounds, macroscopic objects? For now, the vacuum holds these answers close, revealing just enough to tease us with a future where nothingness becomes the most powerful tool in the universe. Think of a vacuum as the ultimate cosmic silence, a space where nothing should happen, where darkness should reign unchallenged. But quantum mechanics has a way of turning impossible into everyday physics. Take the dynamical Casimir Effect, where scientists don't just observe the vacuum's hidden energy, they squeeze real light out of it. This isn't science fiction, it's lab-tested reality, and it challenges everything we thought we knew about emptiness. The trick lies in shaking the vacuum fast enough to rip photons, actual particles of light, from its ghostly grip. Picture a mirror vibrating at nearly the speed of light in a sealed chamber. Normally, virtual particles wink in and out of existence too quickly to notice. But when the mirror moves at relativistic speeds, it distorts the vacuum's quantum field so violently that some virtual photons get stuck in our reality, becoming real, detectable light. It's like slapping a still pond so hard that droplets leap into the air, except here, the pond is space-time itself, and the droplets are photons conjured from pure nothingness. In 2011, a team at Chalmers University of Technology pulled this off using a superconducting quantum interference device, or SQUID. By varying an electromagnetic field at gigahertz frequencies, they mimicked a mirror moving close to light speed, coaxing microwave photons out of the void. The experiment wasn't just a parlor trick, it confirmed that the vacuum isn't passive. It's a reservoir of energy waiting to be tapped if only we can find the right leverage. But here's the catch: extracting energy this way isn't free. The energy required to vibrate the mirror or its electromagnetic proxy always exceeds the energy gleaned from the emitted photons. At first glance, that seems to kill any hope of vacuum-powered futures. Yet theorists speculate that advanced setups like exploiting pre-existing cosmic motion or harnessing zero-point energy differentials might one day tip the scales. Imagine a spacecraft surfing the quantum foam, its sails rippling with vacuum-borne photons, or a reactor humming with energy drawn from the fabric of space itself. The implications ripple beyond energy. The dynamical Casimir effect blurs the line between motion and creation, suggesting that reality itself might be a kind of quantum froth, malleable to the right perturbations. Some cosmologists even wonder if the early universe's rapid expansion could have acted like a cosmic Casimir mirror, amplifying vacuum fluctuations into the primordial light that still echoes in the cosmic microwave background. So is the vacuum a free energy source or just a cosmic tease? For now, it's both a reminder that nothing is full of potential, if only we learn how to shake it the right way. One of quantum mechanics' most persistent mysteries isn't about what exists, but what happens the moment we look. Why does an electron's blurry cloud of possible positions snap into a single, definite location the instant we measure it? The textbook answer, the Copenhagen interpretation, shrugs and says consciousness forces nature to choose. But there's a wilder possibility. What if the quantum vacuum, that seething ocean of virtual particles, is the silent puppeteer behind the curtain, collapsing superpositions without any human observer needed? Enter objective collapse theories, a radical departure from traditional quantum interpretations. These models suggest superpositions aren't fragile ideas waiting for a conscious mind to pin them down. They're unstable by nature, toppling into definiteness like a tower of blocks in an earthquake. And the tremor shaking them, random fluctuations in the quantum vacuum. Picture a pencil balanced on its tip. Left alone, it'll stay upright momentarily, but the slightest air current, a whisper of chaos, knocks it over. In this analogy, the pencil is a quantum superposition, and the air current is the vacuum's ceaseless crackle of energy. The math behind objective collapse theories, like Garrodi-Rimini-Weber or Penrose's gravitational law, quantifies this instability. Larger objects or more entangled systems are more susceptible, collapsing faster because they interact with more vacuum fluctuations. A lone electron might linger in superposition for millennia, but a grain of sand or a Schrödinger's cat would collapse almost instantly. The implications rewrite quantum measurement. No longer a philosophical puzzle about observers, it becomes a physical process as concrete as radioactivity, a cosmic game of chance where the vacuum rolls the dice. Experiments are already probing this idea. Some labs track tiny cantilevers cooled to near absolute zero, watching for spontaneous vibrations that could signal vacuum-induced collapses. Others monitor clouds of ultra-cold atoms for sudden, unexplained decoherence. So far, results are inconclusive, but the stakes couldn't be higher. If vacuum fluctuations really do collapse quantum states, then the universe isn't just probabilistic, it's participatory, with the void itself shaping reality through its invisible turbulence. But here's the twist, this isn't just about measurement. If the vacuum triggers collapses, it might also solve the mystery of why we see a classical world at all. Every atom in your body is constantly buffeted by vacuum fluctuations. Over eons, those whispers could add up, pruning away quantum weirdness until only the familiar, definite universe remains. In this view, the vacuum isn't just a backdrop, it's a sculptor, carving the solid world we know from quantum potentiality. Of course, skeptics abound. Mainstream quantum mechanics treats wave-function collapse as a mathematical tool, not a physical process. And yet, the vacuum's fingerprints are everywhere, from the Lamb's shift to Hawking radiation, proving it's far from inert. Whether it's the hidden hand behind quantum collapse remains an open question, but one thing's certain: the quieter we listen to the void, the louder its answers become. Every cosmic story must end, but how? The quantum vacuum, that silent architect of reality, holds more than just the universe's secrets. It might also script its final act. Will our cosmos fade into icy darkness, shatter in an instant, or rise anew like a phoenix from the ashes? The possibilities are as chilling as they are mesmerizing, each one a testament to the vacuum's ultimate power over existence itself. First, consider the bleakest prophecy: heat death. Imagine trillions of years from now, stars burning out one by one, black holes evaporating into whispers of radiation, and the universe stretched so thin that even atoms drift apart. Space would become a vast, featureless graveyard, its temperature hovering just above absolute zero. This isn't science fiction, it's the inevitable fate if the vacuum's energy continues to push the cosmos apart, diluting all matter and energy into a silent, eternal freeze. Every galaxy, every planet, every memory of life would dissolve into equilibrium, a state where nothing ever happens again. It's the universe's most tragic punchline. After billions of years of dazzling complexity, it all ends not with a bang but a whimper. But the vacuum might have a swifter, deadlier trick up its sleeve: vacuum decay. As we've seen, our universe's vacuum could be metastable, a precarious ledge above a lower energy abyss. If a quantum fluctuation tips it over, a bubble of true vacuum could form, expanding at light speed in all directions. Inside this bubble, the laws of physics would rewrite themselves. Atoms might unravel, forces dissolve, and space-time itself reconfigure into something unrecognizable. The scariest part: this bubble could already be racing toward us from some distant corner of the cosmos, undetectable until it arrives. One moment, reality as we know it; the next, an alien physics overwriting everything in its path. It's the ultimate cosmic reset button pressed at random. Yet not all endings are doom. Some theories paint a breathtaking alternative. The universe might not die but recycle. In cyclic models, the vacuum's energy could collapse and rebound in endless loops like a cosmic heartbeat. Each Big Bang would be the aftershock of a previous collapse, with quantum fluctuations in the vacuum seeding new universes from the ashes of the old. String theory's ekpyrotic scenario even suggests our universe is one sheet in a higher dimensional brain, colliding with others to reignite creation. Imagine it a multiverse where death is just a prelude to rebirth, and the vacuum is the eternal matchstick sparking new fires. Even more radical is the notion of quantum rebirth. If spacetime is truly granular at the Planck scale, as loop quantum gravity suggests, then the vacuum structure might prevent total collapse. Instead, a dying universe could bounce back from its own singularity, like a ball rebounding off concrete. Observations of the cosmic microwave background already hunt for faint echoes of a previous universe patterns that might hint at cycles stretching back further than time itself. So which fate awaits us? The truth is, we don't know. The vacuum guards its ultimate plan fiercely. But here's the twist: each scenario reveals a deeper truth about reality's fragility. Whether frozen, shattered, or reborn, the universe's destiny hinges on the quantum void, the same nothingness that birthed galaxies, stars, and life. And perhaps that's the most profound lesson of all. In the vacuum's whisper, we hear not just the universe's beginnings, but its end or its next beginning. From the infinite churn of zero-point energy to the phantom glow of Unruh radiation, the quantum vacuum has proven itself to be anything but empty. We've explored 30 astonishing mysteries: virtual particles blinking in and out of existence, cosmic strings woven into spacetime, wormholes flickering at Planck scales, even the terrifying possibility that our entire reality might be balanced on a knife's edge above true nothingness. Each revelation peels back another layer of the illusion we call emptiness, showing us a void so vibrant it puts the busiest city streets to shame. Consider the absurdity. This nothingness shapes atoms through the Lamb shift, births matter via the Schwinger effect, stores information in holographic codes, and might even hold the key to consciousness itself. The vacuum isn't passive scenery. It's the director, stagehand, and special effects crew of the cosmic play, orchestrating reality from the shadows. Whether through entanglements, spooky links, or inflation's explosive stretch, we've seen how the void's hidden activity builds the universe we know. Yet the most profound lesson isn't any single mystery, it's the pattern they reveal. Every breakthrough confirms that the line between nothing and everything was always imaginary. The vacuum's so-called emptiness is a hall of mirrors, reflecting back whatever question we dare to ask. Is it an energy source, a computational matrix, a multiverse factory? The answer seems to be yes, and also no, and also something stranger we haven't imagined yet. This journey doesn't end here. Every answered question births 10 more, and the vacuum guards its deepest secrets jealously. Perhaps dark energy is just the first note in a symphony of vacuum phenomena we've yet to hear. Maybe the next generation of quantum sensors or gravitational wave detectors will catch whispers from dimensions we can't yet see. One thing's certain, the universe's greatest magic trick is convincing us that nothing exists at all while hiding everything in plain sight, so keep looking closer. That stillness around you, it's a construction site. That darkness between stars, a living thing. The quantum vacuum isn't empty, it's the most crowded nothingness imaginable. What will we discover next? Let us know which mystery blew your mind the most, and don't forget to subscribe. Because in a universe where nothing is really something, the next revelation is always just one experiment away.